Okay, let's take a look at a few examples where we solve an inequality. Example 1. 2x minus 5 is greater than or equal to 7x minus 3 times the quantity 1 minus x. Okay, so this is a linear inequality, very, very similar to a linear equation, right? The only difference being that symbol right there would be an equals in a linear equation. So the solution strategy here is very, very similar. Try to isolate your x on one side. Now over here on the right hand side you can see there's two occurrences of x that we could combine together into a single occurrence if we just simplify the right hand side. So let's do that first. This of course is 7x, and then distributing the negative 3 we have negative 3 plus 3x, and the 7x and 3x then combine because they're like terms to give us 10x minus 3. And the rest of this just kind of comes along for the ride at this point. Okay, now the two occurrences of x that are left are on opposite sides of the inequality, and we can get them consolidated into a single occurrence if I kill off one of these guys by subtracting it from both sides. We can subtract 2x from both sides, we could subtract 10x from both sides. Both of those would have the desired effect. In truth, subtracting 2x from both sides is probably the wiser move here, because it leaves you a positive 8x on the right hand side, and as we'll see in a moment, that's going to be a useful thing to have as opposed to a negative number times x. But let's go the long way around. Let's subtract 10x from both sides. That's going to give us negative 8x on the left minus 5 is greater than or equal to negative 3. Now you can see we only have one occurrence of x. We just have to undo what's happening to it. It's being multiplied by negative 8, and then you're subtracting 5 from it. Let's undo those things in reverse order. So adding 5 to get rid of the negative 5 to both sides, we'd have negative 8x is greater than or equal to 5 plus negative 3, or 2. And then to get rid of this multiplication by negative 8, I want to divide by negative 8, or equivalently multiply by negative 1/8. However, you have to remember that when we're multiplying both sides of an inequality by the same value, if that value is positive, fine, we can do that. But if it's a negative value, I need to perform the multiplications, but I also need to change the inequality symbol. I need to reverse the inequality symbol. So multiplying by negative 1/8 here will give me x on the left. We'll get negative 1/4 on the right after we reduce the fraction, but this will be less than or equal to. Okay, so don't forget, if you multiply or divide by a negative, we have to reverse the inequality symbol. If you wanted to graph that solution, locate negative 1/4 on the graph of a real number line somewhere. We're looking at all the x values that are less than that. So that would be to the left of that, typically, as we draw number lines. Note also that we have the possibility that x could equal negative 1/4, and so we'll explicitly shade that point in, exaggerating its size quite a bit to indicate that. Okay, so that is our solution. Okay, let's look at a second example. Example number 2. X squared minus 2x is greater than 4x minus 5. Okay, so this is an inequality that involves some quadratic terms, or at least one quadratic term. So what can we do here? Well, again, taking a cue from quadratic equations, the first step there was always to get 0 on one side, to take everything to the other side. And we could do that here too, right? We can certainly subtract 4x from both sides to give us x squared minus 6x is greater than negative 5. That's legitimate. We can add 5 to both sides to get x squared minus 6x plus 5 is greater than 0. Okay, so now everything is on one side. We have 0 on the other side. So again, taking a cue from how we might solve the related equation, the next thing we would do here, of course, is to factor the left-hand side, because we know if a product equals 0, again, we're talking about the equation version here, then one of the two factors has to equal 0, and hopefully finding out where that happens is a simpler scenario. And notice this thing does indeed factor. X minus 5 times x minus 1 would do it, right? There's 5x and 1x to give us a 6x. But we have this not equal to 0, but greater than 0. So certainly this factorization would help if we were solving the related equation, where we have equals here, but does it help here? Believe it or not, it does. First off, notice that because I'm interested in a strict inequality here, whatever values of x would make this equal to 0, I actually don't want at all. Now, what are those values? Well, if this thing equals 0, then either x minus 5 equals 0, in which case x equals 5. I'm going to draw that on the graph here of my number line. Or if this factor was equal to 0, we could solve and get x equals 1. So both of those points are not solutions to this guy up here. I'm going to indicate that with some open circles. But notice, by placing these on the number line, I have broken the number line into 3 separate regions. Now, let's consider any point, say in this region here, from 5 to positive infinity. Any number I put in there, if I'm bigger than 5, what's the sign of that factor? 6 minus 5, that'd be positive 1. 5.3 minus 5 would be positive 0.3. A million minus 5 is certainly still positive. So we have a positive factor there, and then times another factor, x minus 1, what's the sign of this guy? Again, if x is bigger than 5. Well, certainly subtracting 1 is not enough to turn it negative. This is also going to be a positive. So we have a positive times a positive for any value of x in this interval. That's got to be positive. Maybe we just mark that accordingly. Any value of x in this interval makes this whole thing positive. Now, is that helpful? Yes, because that's exactly the x values we want. We want the ones that are bigger than 0. We want the ones that make this expression positive. So all of these guys here are indeed solutions. What about in this interval from 1 to 5? Well, let's see. We're smaller than 5, but bigger than 1. If we're smaller than 5, isn't this guy right here negative? But if we're bigger than 1, what can we say about this? Doesn't that have to be positive? So we have a product of a negative times a positive. That's a negative. Now, is that helpful? Yes, because if it's negative, it's less than 0, not greater than 0. So none of the x values in this interval will constitute solutions to this inequality. Let's see, we've got one interval to go. What if we're less than 1? So like negative 100. If we subtract 5, aren't we negative? Yes. What about this factor? Here again, we're less than 1. If we take anything less than 1 and subtract 1, don't we also get a negative? Even the 0.999 minus 1, it's negative by a little bit. But then you're looking at the product of two negatives, which is positive. And remember, the positive products are the ones we want to keep, because those are necessarily greater than 0. So all of the x values in this interval here are solutions. We've looked at the entire number line. It just remains to write this in a nice way if we don't have to just graph it. So it looks like we have the interval here from everything between 1 and negative infinity, which we could write in the following way. Negative infinity to 1. We use a parenthesis on the negative infinity because we can't ever include that. That's not a value even to be included. We put a parenthesis on the 1 because we don't want to include it either, just everything up to 1. We've got an interval over here, everything from 5 to infinity. Again, we can't include infinity. That's not even a number. And we don't want to include 5 here because that is a strict inequality. Okay, had that been greater than or equal to, we would have filled that circle in and used a bracket here to indicate that. And because we want to say that x can be in either one of these things, either this one or this one, we use the union operators to say, okay, form the set of points that either show up in this interval or this interval. Okay, and so that is my solution. Okay, let's take a look at another example. Example 3. Here, suppose we have x minus 1 times x plus 2 cubed times x minus 7 squared is greater than or equal to 0. Notice the left-hand side has been given to us in factored form, which is a good thing, because if you multiplied this all out, it'd be, let's see what, x to the second and third, that's fifth, that'd be a 6-degree polynomial. We generally don't like to factor 6-degree polynomials. But with it in factored form, it's very easy at least to identify where this expression could equal 0, and that's where we start, just like we did in the last example. Let's draw our number line. If this product equals 0, then one of the factors must be 0. If it's this first factor, x minus 1, well then pretty clearly x has to be 1. If it's this second factor of x plus 2 cubed, then again, pretty clearly x has to be negative 2. If it's this third factor, x minus 7 squared, then again, pretty clearly x has got to be 7, just somewhere over here. Okay? Now, in this particular inequality, we're allowing for the expression to equal 0, so I'm going to go ahead and shade those points in, because those do represent some of our solutions, not all of them, of course. But merely identifying those 3 points breaks our number line into 1, 2, 3, 4 regions. So I want to consider each one of those regions in turn. Maybe we start with the one here on the far right. Okay, so if I pick any value that's bigger than 7, let's see, something bigger than 7 minus 1, that's definitely going to be positive. Something bigger than 7 plus 2, well, that's positive as well. Something bigger than 7 minus 7, that's positive as well. Okay, now be careful here. We found the signs of x minus 1, x plus 2, and x minus 7. We didn't account for whether we cubed things or squared things. Of course, if you cube a positive value, it's still positive. And if you square a positive value, it's still positive. So we have the product of 3 positives, which is positive. Now, does that represent x values that we want to keep as part of our solution set? Absolutely. Remember, we want this expression to be greater than or equal to 0. That means we want it to be either 0 or a positive value. These guys are good. They're solutions. So let's shade those in. Now, let's erase those and start over looking at our next interval. If we're between 1 and 7, okay, what are the signs of these various factors? X minus 1. Well, as long as I'm a little bit to the right of 1, which I would be if I'm in this interval, x minus 1 has got to still be a positive value, right? If I'm bigger than 1 and less than 7, x plus 2, also a positive value. But if I'm bigger than 1 and less than 7, and I subtract 7 from something less than 7, that's going to give me a negative, right? Now be careful, don't just multiply them and get a negative there. This is the sign of x minus 1, this is the sign of x plus 2, this is the sign of x minus 7. We need the sign of x plus 2 cubed and x minus 7 squared. A positive number cubed is still positive, but a negative number squared is positive. So again, we have the product of 3 positives. Again, of course, that whole product is positive. Again, the positives are the things we are looking for. Things that are greater than or equal to 0. So all of these guys also represent solutions. So I'll shade them in. Now, let's consider what happens on the other side of 1 here between -2 and 1. Let's see, if I'm less than 1 and I subtract 1, won't that give me a negative value? And if I'm less than 1 and bigger than -2, again I want to focus on this interval, what's x plus 2 doing? Well, doesn't that have to be positive? Right? Think about negative 1.99, right? It's not enough to make this negative yet, is it? If I have a value between -2 and 1, what about x minus 7? Even at my largest, when I subtract 7, this goes negative. Okay, so the product of these three things, oops, almost forgot. We have to cube that. That's still positive, and we have to square that, right? That turns that positive as well. So the product of these three things is then a negative. Are those x values in that interval going to be solutions to this? No, we want only the positive guys, remember, or the zeros. So none of these get shaded. None of those are solutions. What about to the left of -2? If I have something to the left of -2, something less than -2, and I subtract 1 from it, it just stays negative. If I have something to the left of -2 and I add 2 to it, it's not going to be enough to make it positive. It's still negative. And when I cube that negative, it's going to stay negative. If I take something less than -2 and subtract 7 from it, it stays negative. But when you square that, that becomes positive, doesn't it? So the product of those three factors should be a negative times a negative times a positive. That should be a positive. And here again, those are the values we seek. The ones that make this greater than or equal to 0. Okay? So there's our solution. To write it in interval notation, note this is the interval from -infinity, which you cannot include, up to -2, which we do want to include, so we'll indicate that with a bracket. Or you have an x value coming from this interval, which is from 1, inclusive again, we use a bracket, to all the way up to positive infinity, which of course we can't include because it's not a number. We want to be in either this set or this set. We indicate that with a union operator. And there is our solution set. Okay, let's look at a fourth example. Number 4. X plus 3 to the 5th power times x minus 1 to the 4th power. All of that over the product of x minus 4 to the 2nd and x minus 6. And we're looking for that to be less than or equal to 0. Again, having this 0 on the right-hand side here, just like in the previous example, is critically important, because if you're greater than 0, you're positive. If you're less than 0, you're negative. And so then we can focus our attention only on whether this expression here is positive or negative, which we can do by analyzing each of the factors it contains. Of course, this has factors not only in the numerator, but also in the denominator. As before, we'll start by looking at where this expression is 0. Where does it equal 0? Of course, for a fraction to equal 0, its numerator needs to equal 0, and its denominator needs to not be 0. Well, finding out where the numerator is equal to 0 is pretty straightforward, since this is already in factored form. Either this factor had better be 0 or this factor had better be 0. If this factor is 0, then x has got to be -3. If this factor is equal to 0, then x had better be 1. And sure enough, because we're allowing for the possibility that this expression equals 0, we'll want to shade those 2 points in. Those are 2 solutions after all. There's a larger set of solutions, of course. There are also some values I can immediately exclude that can't be solutions. For example, when this fraction is undefined, when the denominator is 0, that can't be a solution. So letting the denominator equal 0 and solving, of course, that means either this factor is 0 or this factor is 0. If the first factor is 0, then x has got to be a 4. And if the second factor is 0, x has got to be a 6. And of course, those are not solutions, so I'm going to indicate that with some open circles. And we can see we have chopped up our number line into 1, 2, 3, 4, 5 separate intervals. So we just have to do a sign analysis on each one of those intervals as to whether this expression here is positive or negative, and that will tell us whether or not we want to include it in our solution set. Of course, this time we're looking for less than or equal to 0. We're looking for negative values. Now, as we do our sign analysis, it's useful to note when we have a binomial like this one, or any other factor for that matter, to an even power, as we do with x minus 1 to the fourth, and we also have x minus 4 to the second power, those are always going to be positives, as long as they're not 0. And we've already accounted for when they're 0. Okay, so those factors in particular are not going to contribute anything really to the sign of the overall expression. Anything different from interval to interval. They're always going to be positive. So let's look to the right of 6, something bigger than 6. Certainly, this factor is going to be a positive. This factor, always a positive. This factor is going to be a positive always. This factor, if we're bigger than 6 and we add 3 more to it, it's still going to be positive. So we have a positive, a positive, and a positive, and a positive. Everything's positive. The whole product slash quotient is positive. Are those guys that we want? No. We only want to keep in our solution set the ones that are negative, less than or equal to 0. Consider the next interval, between 4 and 6. Say 5 is a nice representative value. Something between 4 and 6, if I plug it into x minus 6, that's going to be a negative. This one over here, x minus 4 squared, always contributes a positive. X minus 1 to the fourth always contributes a positive. And x plus 3 to the fifth, well, let's see. If I'm between 4 and 6, that's something positive. Plus 3 is still positive. Raised to the fifth power is still positive. So I have the product slash quotient of 3 positives and a negative. That's negative. Is that what we want to keep? Yes. Negatives are less than or equal to 0. So I'm going to shade all those guys in. What about between 1 and 4? Here again, if we subtract 6 from something in this interval, it's going to go negative. This is always contributing a positive. This is always contributing a positive. And x plus 3 to the fifth, well, let's see. If I add 3 to something that's already positive, I get a positive. And if I raise it to the fifth power, it's still positive. So again, product slash quotient of 3 positives and a negative, that's going to be negative. And those are precisely the values I want. So we'll shade it in. Looking at the next interval, from negative 3 to 1, if we do the sign analysis, if I subtract 6 from these things, it's got to be a negative, right? Even 0.9999 minus 6, still negative. This thing is always positive. This thing is always positive. X plus 3 to the fifth. Well, let's see. The smallest I might be would be negative 2.999 and so on. If I add 3 to that, that's a small positive. Anything in this interval, if I add 3 to it, it's going to be positive. Again, raising that to the fifth power gives us a positive. So, yet again, we have the product of 3 positives and a negative. That's negative. Those are values we want to keep because we're after the stuff less than or equal to 0. Last but not least, let's look between negative infinity and negative 3. Something that negative is going to stay negative there. This is always positive. This is always positive. X plus 3 to the fifth. Let's see. If I'm less than negative 3, then when I add 3 to it, it's still a negative. And when I take a negative to an odd power, that is also negative. And so now, for a change of pace, I have 2 positives, 2 negatives. The product slash quotient of all those is positive. And those are guys I don't want to keep. They're not less than 0. So it looks like my solution set is everything from negative 3 all the way up to but not including 6, with one exception at 4. Or, written another way, everything from -3 to 4, where we include the -3, hence the bracket, we don't include the 4, hence the parenthesis, and then everything from 4 to 6, where we don't include either one of them. And you can either be in this interval or this interval, so we'll combine them with the union operator. And there is my solution set.